Good afternoon, everybody. Welcome to the next one in our celebration of faculty careers colloquia. And I do know that many of you have heard this before, but I'm taking the opportunity to repeat it maybe this year as well, and then next year we will not. So this is a program that was developed by faculty in the College of Engineering to give the opportunity to senior faculty, full professors, to share with their colleagues, the students, the staff, their experience coming up and becoming a faculty member and a full professor. All full professors are supposed to do this once every 7 years. And then they get the chance to meet with the dean and their department heads to talk about planning for the next 7 years. And so it's really an opportunity to share with everybody what they're doing. And of course today we're very happy to have Professor Andy Weiner, who is going to be our speaker. He's the Cypress Professor of Distinguished Professor of Electrical and Computer Engineering. And I will not go into the details of his bio because you all know him, and you do know indeed that he's very distinguished. And he's going to get to tell us the information, about himself. But I do want to mention that he came to Purdue in 1992, so he qualifies to be part of the series. And so with that, I give you Professor Weiner.
Good. Thank you, Claude. So I appreciate so many people showing up. Thank you. This is the same room where we have my weekly group meetings, and it's a pretty large group. But I think this is even bigger. So anyway, thank you. So I've been interested in what I call ultrafast photonic signal processing for quite some time. Almost 25 years here, and for a few years before that in industrial research and as a PhD student, so it really is pushing a third of a century. So I'm going to share some things, both some of the early things I was involved in a long time ago, and then maybe for about half of the talk, some of the recent main thrusts of what we're doing, and not too much, but a little bit, some of the areas that we're just starting to get interested in. This particular photo is supposed to represent a waveform, and so I gave a talk about a year and a half ago for a McCoy lecture on our work developing techniques for synthesizing arbitrary femtosecond waveforms. The media people who were helping to publicize that event found this wonderful photo, which I liked better than any I had, so I've adopted it for my talks. So I'll go to the following. I'll start off with some introduction, a little bit about ultrafast optics, because this is all about very high-speed picosecond and femtosecond optics. All the electrical engineers know about Fourier synthesis, but what we've done is adopted simple ideas in Fourier synthesis and applied them in sort of an exotic way to light signals that happen to be very fast, femtosecond durations. So I'll just remind you about things that you know that will set the stage for our research work. I managed to find some photos that I liked from a long time ago, so I thought I'd share a brief tour of my early career before coming to Purdue. I'll then move on to talk about sort of really the thing I'm most known for in my career, which is femtosecond Poleshaping, ultra-short pulse arbitrary waveform generation. Even though the main work in that was accomplished even before I came to Purdue, somehow both the technologies and the ideas in there have permeated much of what I've done still to today. So it's fitting to talk about that. And then to the extent that I allow myself enough time, I'll talk about 3 areas that we've been working in recently. That may go in some cases recently as back for a decade, but up through current days. Ultra broadband radio frequency photonics, where we like to use fast photonic signals and use them to generate or process very broadband RF signals, and so coupling the photonic world to wireless. We'll talk about coherent broadband light sources called optical frequency combs from things called microresonators, and so that's taking into the interaction of fast light with nanophotonics. And the most recent thing we've gotten involved in is moving away from deterministic classical short pulses such as you might use in telecommunications, and looking in the quantum world where we can manipulate the correlations between very weak light signals, in fact, correlated pairs of photons known as biphotons. So the introduction to ultrafast optics. Ultrafast optics means fast light pulses and their applications. And a predecessor of the field I was in was perhaps started by Harold Edgerton, the founder of strobe photography from a long time ago. And so Edgerton was the person who really brought forth fast strobes of light at the microsecond scale, which are fast enough to make these beautiful stop action measurements or photos of bullets going through apples, kicking a football, macroscopic, measuring the fastest macroscopic events. And one of the things that very short light pulses are good for, not the main thing I will talk about here, is but measuring much faster events that happen in the micro and the nanoscale. So the energy exchanges of electrons in lattices, fast molecular vibrations, and so forth. So I won't go all into this, but I do want to establish the time scales. And so moving on back from Edgerton's microseconds, we have time scales of somewhere between nanoseconds and picoseconds, whereas is where electronics gets to. But in nanoseconds, we have 10 to the minus 9 seconds, a bunch of zeros followed by a 1. And in spatial coordinates, we can think of a signal traveling at the speed of light in 1 nanosecond goes about a foot, 30 centimeters. So a picosecond, 10 to the minus 12 seconds, or a trillionth of a second, is 1,000 times faster, and it corresponds to a distance scale about 0.3 of a millimeter, or the thickness of a business card. And so in ultrafast optics, we're really talking picoseconds down to femtoseconds, and these days beyond. A femtosecond is 10 to the minus 15 seconds. Spatially, it's 0.3 of a micron. I'll come back to that in a moment. That's sort of at the limit of visible light or laser technology. At a femtosecond, we're as fast as a single optical cycle. But for the last 10 years, this is not an area I've been involved in, but one branch of research has moved into vacuum ultraviolet X-ray wavelengths where the frequencies are higher. You can support more bandwidth in shorter pulses, and the research frontier is now in the attosecond regime. So there are a lot of applications ranging from putting energy in materials very rapidly to improve the quality of laser machining compared to what would happen with slower nanosecond type pulses. There's been a Nobel Prize awarded for using fast light pulses to time resolve the first steps in photochemical reactions, and in some cases there are a lot of efforts to go beyond that and to try to control at least simple chemical reactions. Areas I've been most interested in is the intersection of fast light signals and I'd say things related to transmission of information. So fiber communications for many years, and more recently, the intersection of light systems for controlling even wireless signals. So just a little bit about the background. First of all, how do you make short light pulses? Just one slide on this. And I'll have several animations here, and I think these two current, still present graduate students were making the little movies. But a review of what a conventional continuous wave or single color, single frequency laser is. It's an optical oscillator, meaning it's a gain element, which happens to be an optical gain element, enclosed in a resonator or a cavity. And so here represented as two mirrors with the idea that any light that's in there that goes back and forth between the mirrors is amplified each time. And provided the amplification exceeds the round-trip loss, for example, due to the imperfect mirrors, strong light beam builds up essentially out of nothing. Some of it's transmitted through a partially transmitted window, and you've got a laser beam. So typically, these have a very constant output in time. They're single frequency. Technically speaking, we say it's monochromatic. In the short pulse field, we actually try to work in a quite opposite regime. And so instead of having a single frequency laser, it's actually a laser with as many frequencies as possible, all working together in a coherent way. From the time domain point of view, what you have is a similar arrangement, but with a periodic shutter of some sort inside there. And with the idea, or a modulator, with the idea that if the light is going through there, when the shutter is closed, the light gets attenuated. So a burst of light goes through, probably a pretty long burst of light. But then going back and forth many, many times, it may get shorter and shorter until it reaches some very short, steady state. And that can be, what we really think of as a modulator drive externally, or in the most successful cases, very popular, is something that's nonlinear. And we'll talk on and off about nonlinear optics here, where the intensity of light affects the property of a medium or device, and that, in fact, turns back and affects the properties of light. and so cases where the intensity of light can influence its transmission and make a self-actuated and self-timed shutter. And in the course of going through many times, pulsing it shorter and shorter into the femtosecond regime, we end up with some periodic train of pulses that are emitted once every round trip through this laser cavity. And so we have periodic short pulses made up of many frequencies. So what I've been very interested in for a long time is using those phase-locked frequencies and manipulating them to make waveforms that could be short pulses, but could be many other things we may be interested in for an application. And so, of course, the popular analogy is music, which is made up of many frequencies that are combined in different ways. And in electrical engineering, of course, we study Fourier series, Fourier transforms, and so forth. And this simple picture showing 1, 2, and then 5 tones of harmonically related sinusoids, we can see that they may start to build up in overlay in patterns, and where they reinforce each other, for example, you may start to get a pulse. Okay, so if we look at now this Modloc laser picture, there's our periodic pulses, and depending on the number of frequencies and what their spacing is, the Fourier transform will give us a train of pulses with different spacings and different pulse durations. Interesting thing to notice, as the repetition rates get longer and longer cavities, the frequencies get closer and closer together, and they start to merge into a continuum. In a real Modloc laser, we may not have a few dozen lines, but we may have 10 to the 5th to 10 to the 6th lines. And so when I talk about waveform synthesis in a little bit, for most of the time this was done sort of in the continuum limit, where we ignored the fact that we had individual lines. We just viewed it as a glob of frequencies. And the result was we manipulated pulses sort of in isolation. Later on, I'll show how we got to the point where we actually look at the individual lines and make waveforms that somehow are coherent across many cycles as opposed to being isolated. So what I'd like to do in my career a lot is to play with phase, and so in these cases all the phases of the frequencies would be the same, but playing with phase is very powerful. And so in this animation involving only 2 frequencies that are say omega and 2 omega, is showing what happens when the phase simply changes. So the 2 harmonics move across each other, and clearly the time domain waveform changes in interesting ways. You can go beyond that, and the sort of class example is Fourier synthesis of a square pulse signal. And so here is showing a case of 31 harmonics, which are turning on one at a time. And as you get more and more of these 31 harmonics, you start to make a square better and better. So sometime soon, maybe after a little detour through some of my early photos, we'll talk about doing this in the femtosecond time scale with light signals. Okay. One other thing I want to introduce is the notion of dispersion. And so if we really want a series of short pulses, we want a bunch of frequencies that all have the same phase and are locked together in that way. But we can have many different relationships, and one thing that happens when a pulse of light travels at a medium, such as an optical fiber or a piece of glass or what have you, is the different frequencies of light have slightly different speeds, and the different frequencies spread out. And we call that dispersion or group velocity dispersion. It's equivalent to having picking up a phase versus frequency characteristic that is not flat, but is a quadratic function of frequency. As that gets stronger and stronger, the tilt of sort of time versus frequency becomes stronger and stronger, and our pulse, as it's traveling down the medium, starts to spread out and the colors start to separate. So that will come up several times really throughout the talk. Okay, so here are some of the photos. Again, I looked around to see what I have, and I had exactly 3 from graduate school, 2 in the lab and 1 of me, and that's probably the proper proportion. But so I was at MIT from 79 through 84. This was the title of my thesis, and so it was some femtosecond optical technology and some early attempts at applications of measuring fast material properties. So this is a time period of about 10 years where I would say I was in love with something called a colliding pulse Modloc ring dye laser. It had the advantage that it was very photogenic. We were working with visible light pumped by green light from an argon laser. There were these fluorescent dyes that are laser medium, and they kind of glow yellow somewhere around here. And the part that's actually a laser beam, you can just see in a few places are these red glows where light's bouncing off the mirrors. So the background here is I had signed on to a new professor who'd come up to MIT from Bell Labs, who was one of the pioneers of short pulse lasers. He was responsible for, together with another Bell Labs guy, for the shortest pulses at the time, which was about half a picosecond. And so I agreed to build up one of these dye lasers once the lab was ready, which took about a year longer than I thought. In the meantime, his colleagues at Bell Labs had figured out for the first time how to get down to 100 femtoseconds, and decided I would try to replicate that once our lab was ready. And I managed to. It took about a year. There's a lot of black magic and things that weren't understood, so there's a lot of not very well-directed fiddling. But eventually, I had, it's not quite clear, but the first, or one of the first for sure, 100 femtosecond class lasers in a university. One of the things that I and a colleague ended up doing, sort of the technology side, is saying 100 femtoseconds wasn't short enough. And there are a number of groups who got involved in trying to make them shorter by a nonlinear pulse compression method. And so the idea was to take a short pulse that goes in a fiber. This was only 8 millimeters of optical fiber. And it turns out through the nonlinear refractive index, the light changing its index, which modulates the phase, you could get spectral broadening, which is what's shown here. But in our case, we got about a factor of 4. And more bandwidth means you could have a shorter pulse if you can just put the frequencies together. Turns out a way to do this are this thing's called a grating pair. These are diffraction gratings. For those of you who don't know optics, it's sort of the front end of a spectrometer. And gratings are used to separate the colors of light. But used in pairs, they can also be used to separate light not in space but in time. And so we're able to compress pulses by about a factor of 4. And for a fraction of a year in my senior year as a student while I was interviewing, we held the record for the world's shortest pulses.
Was it the Guinness record book?
It was the Boston Globe and the New York Times record book. And what was interesting, so these are some articles. I just noticed something when I was putting this together I never noticed before. So Boston Globe on May 25th, New York Times on May 26th. And what they tell us, this is the spatial scale again. They had an interview with my thesis advisor, Eric Ippen, and I'm sure they didn't get it quite right. But they said in a second, a pulse of light, 1 femtosecond long, travels 2/10,000ths of an inch. That's about 5 microns. So that's wrong. Okay, it's wrong by about a factor of 16, which are a pulse duration. And what they must have really been told, it was a 16 femtosecond pulse, which we had made, travels that far. In 1 femtosecond, it travels that far. And what was interesting is the Boston Globe did it the next day. The New York Times got rid of most of the article, but kept the erroneous fact. So I got a kick out of that. So on to Bellcore, and I didn't count here, but there's a challenge, if you could see all these photos, how many different types of mustaches I had. But, so what Bellcore was one of the first clones of AT&T Bell Labs. 1984 was notable because of George Orwell's book, because I graduated, and that was the first time the Bell monopoly was being broken up. And out of that came a new sort of mini Bell Labs, which is called Bellcore, Bell Communications Research, which the regional phone companies were allowed to do one thing together, and was to have a central research organization. And we were actually given these desk plaques. I couldn't find one. Dan, do you have one? That said our goal is to be the world's best telecommunications research organization. And for at least a few years, I think there was a pretty good effort to do that. It was the endeavor lasted probably a little bit less than a decade. But so here are some pictures, and in that 8 years there, I ended up having 3 different laboratories in 2 different buildings, and they kind of got progressively bigger. But so here are different pictures of me as a young guy playing with different sort of laser setups. That big long laser is an argon laser. It put out 10 watt of green light, takes 38 kilowatts to drive it, and several gallons a minute to keep it from burning up. Lasers have gotten a lot better since then. I like this one because it shows no, not laser goggles, but this was a joke. These are sunglasses, which won't protect me. But anyway, you're not an expert, maybe you can't tell.
Just to look cool.
This was another one. This was probably very early when I had a lab going, same sort of dye laser. I thought was interesting is this photo was brought to my attention in 2013 by one of my students in my group, who says, I saw a photo of you in Optics and Photonics News advertising the National Photonics Initiative. I'm sure the National Photonics Initiative is talking about optoelectronics and not giant lasers, but there's a few photos like this that are on the web and they just keep coming back. So there'll be another one actually. Okay, so a little bit seriously, what we are why do they hire me to do femtosecond pulses at Bellcore? Well, I think one of the reasons is fibers were clearly on the way. They were much less mature than they are now. We couldn't even make light at the right wavelengths very well. But fibers, as introduced by Charles Cowan in the late 60s, and he won a Nobel Prize 40 years later, glass waveguides are superb carriers of light. And this is a plot of the loss going through a fiber in dBs per kilometer versus wavelength. This is really a fairly recent one, but it wasn't too much worse except for this bump over here, even a few decades ago. And the idea is you can get about 0.2 dB per kilometer of loss. So times 50 kilometers, you lose 10 dB or you have 10% of your light. Compared to, say, working at gigahertz frequencies on copper or other cables, you get hundreds of dB per kilometer loss. So at a kilometer, it's completely opaque. And so for long distance, high speed transport of information, fibers are very, very good. And our motivation was simply that there's different measures of the bandwidth. This is, for example, an optical amplifier that didn't become available until around 1989. But even that limits bandwidth, but still gives you 10 terahertz. So there's a lot of bandwidth. It's being squeezed pretty hard now. But we had the idea that one thing you might want to do with all this bandwidth is put short pulses, which could be about as short as 100 femtoseconds, and learn how to solve all the problems that would be involved as using them as bits in a light wave communication system. So that was our very broad sort of scientific charter for doing some of this work. So here's an example. This is together a nice photo. This was from the Bellcore annual review, and the main thing we'll see is I've got a lot more lights here. Okay, so we've got one of the laser systems in this yellow box over there. There's also an amplifier system to make them more energetic, pumped by something called a copper vapor laser. It was pretty powerful, but just think, copper is usually a solid. There's a lot of electrical power going in to make a laser based on copper vapor. We actually brought one here when I came here, but put it in a warehouse with the hope we would never have to use it, because I was afraid somebody in a university environment would get killed. We never did that experiment. I never had to. We never had to use it. But and by the way, why do I look glassy-eyed? Because it takes a long time to make a photo like this. Basically, visualize the beams. There's somebody with a black glove on, sort of crawling around in the background with a liquid nitrogen hose. And as the gas comes up, it gives you some scattering, so you kind of have to trace out the beams. But what we were doing is we were demonstrating what at the time was called the world's fastest switch. It was a 100 femtosecond switch. It was using this giant laser apparatus and putting into one of the two light guiding cores of this dual core fiber. This was, again, 5 or 8 millimeters long. Each of those two bright spots were very small high index regions that can confine light. Normal fibers only have one core. But if you have two cores close together, light can slowly couple back and forth from one to the other. That's called a linear coupler. And if you break the symmetry, for example, with high intensity light, it frustrates the coupling. And so you can make a switch basically where, depending on the intensity of light, it comes out one light guide or the other. This was an early demonstration of that, so we were the first time to show that something like this could respond in 100 femtoseconds. It's a little before our time, though, because it's a little tiny fiber, and it took a giant laser like this and peak powers of 50 kilowatts to make it work. This is why we were the first to be able to do this. It was hard to actually have the fiber technology and a sufficiently giant laser. Okay. The other interesting thing, you probably didn't notice it, but there's a person hiding back there. I didn't even notice it until I read the caption of the book and saw there's a guy named Dan Laird who's sitting in the back over there. And so Dan, at that time, had recently got his bachelor's degree and was working with me for a couple years. When I came here, he decided to return to his home state and get a PhD in his state as a very valued research scientist. And so that's then and now. This is another one of these magazines, photos that keep showing up. A couple years after I was here, I looked in my mailbox, and for 1 year, I had a subscription to Proceedings of the IEEE. I don't think I ever read it, but I looked at it and said, there's something familiar about that photo. I said, I think I know that person. Oh, I think that's my laboratory. So, whatever. So, okay. So what are some of the other things we were working on? So we're interested in a lot of nonlinear optics and solitons, and I'm probably not going to get that far, but if I do, some of this will come back recently. But so these are sort of nonlinear bullets of light, either in space or time. In the spatial domain, we're doing experiments where we're putting light in sort of planar type of waveguides, little sort of sheets of glass, if you will. And at low power, we get this little spatial beam of light out, a few 10 or 20 microns, I forget, sort of says over here that we could look at. That was the input, but if you look at the output, light likes to spread. That's called diffraction. And so we would get this spread beam of light. But if you crank up the power, the nonlinear refractive index, the light increases the index of the glass and makes its own waveguide. And so the light then can sort of be preserved in the same spatial duration. If you turn up the power more, it spawns several of these are what are called solitons. So those are called spatial, one of the early works on what's called spatial solitons. So these can, very equivalent things can happen in time. And there what happens is a low power pulse of light will spread out due to this dispersion I mentioned. But with proper intensity, you sort of make your own kind of guide in time and the pulse gets preserved. That would be something called a bright soliton that happens in infrared wavelengths where we do telecom now. But at the time we didn't have any lasers there, and in the shorter wavelengths, dispersion has an opposite sign. What was faster becomes slower. And you can have these things called dark solitons, which are backgrounds of light with a hole in the middle. And with Poleshaping, I'll tell you about, we were the first to be able to make these holes. And we were able to do experiments that look sort of like this, but here the feature, the input is a narrow dark pulse. At low power, after you go through a fiber, this was only meters of fiber, it spreads out. And at higher power, it progressively gets narrower and eventually spawns additional sort of weak solitons. So I'll show that because, again, I may not get there, but if I do, after about 25 years, dark solitons have come back into our laboratory in the work we do on microresonators. So maybe one more here. So now I'm going to go on to pulse shaping applications. And the way we got into this was within really the first years at Bellcore, I got involved with a senior collaborator on another pulse compression experiment. But now we had a laser that wasn't very good at making pulse. Instead of 100 femtoseconds, was 80 or 100 picoseconds. But it was something called a Newton-Yag laser that instead of making milliwatts, made 10 watts. So it was interesting to try to make this high power laser, sort of industrial quality laser really, much shorter. And so here we had fiber. Instead of millimeters long, it was hundreds of meters long. Here we had these gratings again. Instead of being this close, we're kind of a meter apart. And we noticed that now gratings are doing what they normally do, which is also spreading out colors of light in space. That's how you build a spectrometer. And so it turned out when we compressed these pulses, which were compressed by about 100 times compared to where we started, which we were pretty good about, but just some intensity didn't quite go back together. And we recognized that from the particular way it happened, that these offending frequencies that didn't like to compress were the highest and lowest frequencies, which were sort of on the edge of this beam here. And so we did something called spectral windowing. You put in a razor blade in both ends, you chop up a few frequencies that don't compress, and you generate a much cleaner waveform that really comes down in a rock solid way. So that was a very simple idea, but what it quickly turned into is we realized there was old possibilities of doing Fourier synthesis. If you truly really spread out frequencies of light, then you could go in and spatially parallel way, control amplitude and phase, and make whatever you want. And so then we started doing things like this that start just with a short pulse from my beloved femtosecond dye lasers. We had some gratings that we did in such a way that we could have a mask or modulator array later inside, control amplitude and phase, and we could, in a completely intentional way, turn a single pulse into, say, a femtosecond data sequence, into pseudo-noise signal that might be something you think of in spread spectrum communications. You could reverse that later, and essentially anything you want. Originally, these were with microfabricated optical transparencies, well, either metal ones that had pattern transparencies, or you can't see this very well, but these were a series of bumps that give you different phase. You could put them together and make fancy waveforms. With a few years, and Dan was working with me at that point, we worked with colleagues and started to use essentially simple liquid crystal things similar to liquid crystal displays to make programmable masks. That sort of shortly took over, and really the programmability became an enabler, now allowing many people to jump on this technology. It also allowed you to do not just binary phase, which we could do here, but continuous phase, which is really what interested me. At that time, I didn't care if anybody else could do it, but it turned out fortuitous that lots of people could and really kind of sort of help push the technology along. So this has been used a lot for things. I'll just illustrate some of our interest after a few examples, and again, things related somehow to information. Okay, what does it look like? So now we've moved to Purdue at Bellcore. We didn't have infrared lasers. We weren't doing anything. We weren't doing anything with at least telecom type fibers. So we got interested in that at Purdue, and so here's in the early 2000s a setup. Now with commercial spatial light modulators are available, based in part on our early designs. We can come out of little glass fibers into free space. Artist's conception of where the frequencies might be. We could go back, and in fact, we fold it back into the same fiber that sort of saves space, but the real thing we discovered is originally in making these Poleshapers, it was very hard to do. It could take actually weeks to get a good alignment. Okay, there are a lot of degrees of freedom. And actually, a simple trick of having a mirror that sends a thing back into where it came from takes out a lot of degrees of freedom. And then we got at least an experienced graduate student could put one of these together in the afternoon and make it useful. And so that wasn't anticipated, but was very welcome. In the meantime, this sort of technology has entered fiber optic mainstream communications, where you not interested in short pulses, but you're interested in many wavelengths of light for different channels. You'd like to be able to individually, independently play with their intensities, actually do different switching functions. And so a lot of very nice technologies got built up for that application. And they may look like boxes like this, or even smaller if they are going in kind of beyond research systems when they're the real deployed ones. But about 5 years ago, some folks were involved in that, and some university partners in Australia realized they had a platform that could do phase, which is what we always wanted. And once they did that, they said to have an instrument that's a very nicely engineered, thing that is beautiful in research labs. So we have more of these now than home-built Poleshapers, which is quite a change. And just some examples, we can play with 5 terahertz of light and 500 programmable channels and 10 gigahertz centers, amplitude phase. You can really have very powerful control. A couple examples. So one is, this is background, just in case anybody doesn't know about Young's diffraction experiments. But this is one of the classic things that sort of shows that light is a wave. And a particularly interesting one is the two-slit experiment, where light goes through. And if you look at after it diffracts or propagates to the far field, it's not just 2 stripes, but it's this beating pattern. Okay, so this is really taking a Fourier transform operation. So we were able, this is back in the Bellcore days, in fact, to do this in time, not in space. And so in this experiment, our mask was simply killing all the frequencies in a broadband spectrum except for 2. We could play with phase as well, so those 2 could be phased or anti-phased. And then you measure the fast waveform, and depending on each of these 2, you get these nice beating patterns, so that's sort of Young's pattern. And by the way, we could phase shift it by controlling the phase of the light. We could also come back and make the classic square pulse in Fourier synthesis. And so this is again before any programmable devices, but we could design masks with the appropriate intensity transmission function. Looks something like this. Here's a slightly different one that gave us something like plus or minus 13 well-controlled side lobes to try to make a sync function. Throw a phase mask on top of that, and you start to make a 100 femtosecond class input pulse to look like a pretty good square that agrees with theory. A lot of other examples. So what I'd like to do now is start to look at some of the applications and research areas. So one that I've been interested in for a number of years, and this was kind of a relatively, first time I got into this was probably about 6 years after I got to Purdue, and we revisited it a few times. But it's now to use this as a programmable dispersion control device. If you send a very short pulse over fibers, it spreads dramatically, different frequencies spread out. And by the late 90s, the commercial light wave communications was getting good enough that it wasn't just femtosecond people were worried, but if you had a 10 gigabit per second light wave communication system with 100 picosecond bits, this spreading got you in trouble maybe after about 40 kilometers, and so limited transmission distance. And so for that reason, people invented fibers that had different signs of dispersion so that you could have one fiber that spread out the frequencies in time one way, and another fiber that would have roughly the opposite characteristic and put them back together. So we got interested in what the short pulse limits were. If the pulses are too short, then the mismatch between these fibers or higher order variations of delay versus frequency become important, and you get a little distortion. And we said, let's fix that. And the principle is something I call a spectral phase equalization. So basically, one of the simple Fourier things tells us that if we have a phase versus frequency function, if you take the frequency derivative of that, you get a frequency-dependent delay. And the frequency-dependent delay is exactly what we're worried about. And so the idea is we can create frequency-dependent delays that compensate for distortions that we measure by programming a certain frequency versus phase versus frequency function. Okay, so that's what I'll show you in the next 2 slides. This is sort of the first time we looked at that. When these dispersion compensating fibers were pre-commercial, we were able to beg one from a colleague at Bell Laboratories, and students would literally kind of unroll it in the corridor and try to, with a meter stick, and try to measure out the right amount. And so we were able to do a couple kilometer type of experiments. And so here's an input pulse, 500 femtoseconds. We went through 3 kilometers total of one of these compensated links, pulse spread several hundred times, which we don't show, and the dispersion compensating fiber almost carefully measured, puts it almost back together. It's a little bit of distortion. Turns out an ultrafast optics person says, oh, that ringing is a cubic phase versus frequency characteristic, mostly. So you dial in, these were 128 pixel devices, here's phase, it should say pi. So this turns out was the best characteristic, cubic plus a little quadratic. You do that, this turns back into this. Within measurement error, it's distortionless. And this is the first time somebody had done an experiment like this. Fast forward 2 more iterations of this in 2004 to 5. Now dispersion compensating fibers were very much more optimized. You could buy modules in a little box that were designed for this compensates 25 kilometers, this compensates 50. They're much better matched. And so we were able to go out to 50 kilometers. Otherwise, it's the same sort of experiment. Half a picosecond in, now it spreads out 4 orders of magnitude to 5 nanoseconds. Dispersion compensating fiber brings it back to maybe 99.8% goodness. So at about 14 picoseconds, that's this black thing here. It's still not very satisfying. And we were able to program on first quadratic phase, which is a length mismatch, then a cubic phase, which is a mismatch in some of the actual propagation characteristics, and eventually get back to this red curve, which is again indistinguishable from the input. To give an idea of the complexity of what we're doing, this is the phase versus pixel or frequency, and if you unwrap it, you get about 100 radians of phase, but you can do it, with the precision that you need to really have very beautiful control over the light wave signal. Okay, so let me launch into the first of what are some things we're doing now. This is the oldest of the ones I'll tell you, even if I tell you about all of them, which we started probably about 12 years ago, okay, and is becoming so good now that I'm kind of questioning, is we're either going to find some real applications or we're going to say it's done and move on to something else, and that's a little bit unclear now. But the idea is that electronics is wonderful, but if you really try to give a lot of bandwidth, even though it keeps getting better, it doesn't have the bandwidth that optics does. And so the idea is if you wanted to make really highly structured broadband waveforms, if you use an optical front end and then use a fast enough photodetector, you could take our Poleshaping capability and turn it into some very broadband radio frequency arbitrary waveform generation capability. So there's different schemes, but the most successful one, as I say, is you actually shape not the pulse itself, but you shape a spectrum. Here's a spectrum, you cut out some intensities in a pattern you want. Now you use one of these dispersive fibers, not as something to fix, but as a tool to spread the light from femtoseconds to nanoseconds, and to stretch this pattern in frequency into a corresponding pattern in time. So this is down in nanoseconds. So this is our sort of first paper on this from probably like 2004. In the meantime, the technology got better and understanding of how do you really program this to get exactly the right waveform. There's some interesting waveform design things to get it right. We were able to, maybe one of my current students or one of the people he worked with, I forget exactly who's this. It's one of my Amirs, but I don't know if it's a present Amir or one who graduated. You both did this. Okay, so we can make, for example, here's a 41 gigahertz chirp that goes from like 2 to 43 gigahertz or something. There still aren't any electrical boxes can do that now. They can't do this. You can see we can make almost exactly what we want. So we can make very complex signals. Some of the other things we're doing is trying to say, well, can we go to higher frequencies? Until recently, sort of 60 gigahertz was about the limit for commercial photodetectors. So we recently, in the last 2 years, had a collaboration with a group in Taiwan that does experimental photodetectors. It goes to 100 gigahertz. This is called a Wband, 75 to 110 gigahertz photo mixer. You send light on, you bias it, and you get an electrical signal out, which is now just not launched into a scope, but is launched into a series of waveguides. It goes through power amplifiers, and we launch it into free space with these horn antennas. Typically, they'll be separated by about the size of my largest laboratory, which is about 6 meters. So we're starting to do wireless. And we can make various things. This is an example, if there's any radar people here, this is called a Costa sequence. It's just a sort of one example of a desirable frequency hop signal that hops 1 gigahertz steps. We have 15 of them in sort of 1 or 2, 1.5 nanosecond or something windows. Now you can actually see this because we measure in a real-time scope that goes from 0 to 20 gigahertz. So it looks a little bit slow, but the way you do that is you have a down conversion mixer where you mix it with essentially a 78 gigahertz signal to bring it down to baseband, or you can measure it. And to measure the whole spectrum, we have to measure it in several sequences and reconstruct the waveform. But it's a nice signal, it's a nice auto-ambiguity function. There's many more things you can make. We also started to look at ranging. If you allow bandwidth, you can have good range resolution. And so this is an experiment where we have a transmit and receive antenna. I'm not sure which is which, but we go off some targets and come back. And now the farthest target is probably 4 or 5 meters away. And you can see here's a sphere that's pretty close, and then there's some plates that are further back. Two of these plates are very close, so we can really look at the resolution. And this is simply showing, here we're looking over, sort of the end of 50 nanosecond type of range. We see 3 peaks, and one of these peaks, if you blow it up, is actually, here it's 1 peak, because those two, probably one of the plates is missing. But if you put the second plate there, you can actually resolve these guys down to about 4 millimeters, which is the best we've seen in this frequency range. Okay, so just one sort of thing we play with. This also is the first case where I got involved in this, is together with Professor Minghao Chi, but into bringing this sort of signal processing with optics into the nanoscale. And so this is, I think, really an area that's become much more active and is one of the ones that's going to stick around. But here we're trying to make simple spectral pulse shapers for getting rid of the bulk pulse shaper on a silicon photonic chip. And so what we did, or what Minghao does, he's the guy who actually knows how to make these sort of things. There's a series of rings coupled to a waveguide, and each one's a resonance. Each one is a resonator that can essentially take out light at a selected optical frequency. And it's not shown in this cartoon, but you can put on these resistive heaters on top, which allow you to shift the resonances. And so you end up taking a signal where you can put out little notches out here, or in a different waveguides, all become peaks. You can move these peaks around in the spectrum. With some interferometers that have thermo-optic heaters, you can turn the features up and down. And so you can make some interesting spectral features that we stretch in the fiber just like we did before, and then photodetect, and we start to make some waveforms. These are simple chirp waveforms going up chirps or down chirps using this technique. Okay, well, oh yeah, there's more here. So this sort of got us a little more into wireless, and so one of the things we became aware of once we could make arbitrary waveforms is, okay, what can you do? And when we were doing this, there was a lot of discussion. It was a fairly new topic of something called ultra-wideband, which was a 3.1 to 10.6 gigahertz wireless, unregulated, sort of short distance communication type of capability. And so that's actually a lot of bandwidth. RF people usually may tune over wide bandwidths, but they don't have all the bandwidth at once. If you have all the bandwidth at once, it sort of demands a short pulse perspective, which we bring. And so it turns out there's a lot of antennas, not all, but a lot of antennas that can cover very wide frequency bands. These are probably 2 to 12. We do some with 2 to 18 gigahertz. But they're not optimized for pulse response. In fact, we would call them as highly dispersive. Different parts, different frequencies come out with different delays. And so this is just an experiment with a 1 or 2 meter link between two commercial antennas that are highly dispersive. And so here, if we come in with about a 200 picosecond impulse and some background we won't worry about, it spreads by about a factor of 10. In fact, due to some of the details of how the antennas are made, their bad pulse response. And so what we do is we say you should fix that. And so we can make waveforms that are essentially flipped versions of this. At least the sort of frequency variation is flipped. We can tailor it. We can make the pulse self-compress approximately to the bandwidth limited duration. Because that was the first time anybody had done an experiment like this with broadband antennas. So we did some more of that. Some of this early work was with Dimitri Paroulis as well. And we decided we should look at a harder problem, which was not line of sight environments, but high scattering environments, which is how most wireless communication happens, certainly indoors. And so the simple picture is I have some transmitter, maybe it's making a pulse. I transmit it, here's some receivers, but it goes through we're going to go through a wall, we're going to bounce off all kind of things. And we have this highly multipath, realistic environment. And so instead of getting a pulse out, we get something like this. We just get a whole series of essentially random echoes, random phase, random amplitude. It can be very complex. If you move the receiver a little bit, you get something that may largely decorrelate, have similar structure, but it's a different, let's say, a kind of a random time signature. For any of the wireless people, if you look at the power spectrum, it has these deep fades that you always get when you have multipath scattering as well. And so we say, let's try the same thing. This is more challenging from the waveform design point of view because these are really complicated. So they were kind of a good incentive to make better waveforms. But say, let's make a flipped version of this again or do something similar to that. And if we do it right, this should self-compress in whichever receiver we design it for. and it should remain uncompressed in the other one. So we should even have some private communication possibilities. So we've done this now, both with electronic waveform generators or for more bandwidth with photonic ones. I like to show the photonic ones because this is a photonics talk. So here's an example where we're using 2 to 18 gigahertz antennas. Again, we're doing communications between simple transmission between different rooms. Sometimes, I think this was one room, sometimes we do 2 rooms. And so here are 2 different impulse responses, 2 different receivers, a few different tens of centimeters apart. And what we can do is we can dial up a waveform to compress this one here at the receiver while leaving this one essentially noise-like. Or we can say we like this one and dial up a different waveform that compresses here and not over there. And so at least over sort of these type of bandwidths, we think this is kind of unique as well. Okay. So there's analogies in optics. This is something new. My student here, Bo Halu, I've sort of tortured him by trying to get him to start doing this for us. But so we're interested in bringing this back to optics. This is a picture and just sort of a little introduction article I wrote a couple years ago to somebody else's nice work. But it's describing what I call space-time speckle in optics. And so the idea is anybody who does optics knows if you have some coherent light and a scattering media off a piece of paper, whatever, you get all this speckle, this bright and dark sort of random pattern. It's coherent interference. And some time ago, like about 15 years ago, I got interested in this together with Kevin Webb, and for a while, for quite a number of years, we had a nice collaboration, trying to understand not just spatial speckle, but what are the time and frequency correlations. And so the idea is it's a lot like, I think of it now, it's a lot like wireless transmission. Short pulse comes in, it should randomly scatter, and if you look at any output spot, it's not only brighter or darker, but there'll be a different temporal substructure and a different kind of frequency substructure as well. So this is actually a hot topic in optics. Mostly in the spatial degrees of freedom, people manipulate the input light signal to try to get some compression, usually in space. And so we're asking, maybe can we find a way to do this in space and time together? And so some people do this for biomedical imaging, but we're interested in optical fibers. And so we just sort of started characterizing multimode fibers that are essentially large core fibers that have different modes of propagation that are associated with different delays. So it's like a multipath system. And the simple thing we're doing here is sending a single frequency laser through that's tuning 0.1 nanometers at once, or gigahertz, and looking at the speckle pattern at the output. For the long fiber, as we tune the wavelength, the change is sort of really changing very fast. For the shorter fiber, it's only slowly evolving, and it's sort of relationship between the frequency, the scale, the frequency correlations, and how long the kind of temporal delay spreads are. And so we're trying to see if we can control this enough that we can actually start to now make structured light at the input and compress or make desired time-space patterns at the output. Where's it going to take us, we don't know, but potentially there's communications applications. People use these fibers for comm, probably not so aggressively, multimode, and they use it for bioimaging as well. So we'll see where that goes. So I'm going to, there's 2 more topics. I'm going to hit one here. So I'm going to talk a little bit about line-by-line shaping and microresonators. This is really the biggest topic in my lab now, and certainly one the government has been most interested in pouring money into. Okay, so a little bit on line-by-line shaping. I introduced this before, is that most of this Poleshaping ignored the fact that Modloc lasers have discrete frequency lines, viewed as a continuum. Well, this came to the fore around 2000 when these 2 gentlemen leading efforts at NIST in the US and in a large institute in Munich, their groups showed that you could have a Modloc laser and you could precisely measure and precisely stabilize the frequencies of all these. So usually there was a grid of frequencies that was left to sort of drift around. They learned how to take out that degree of freedom so well that it could be taken out to like 19 digits. And so this completely revolutionized the ability to make precision frequency metrology, comparing against different frequency ranges. Within about 5 or 6 years, there was a Nobel Prize for this. And so this attracted a lot of people's attention. And basically, people are trying to make frequency links between RF and optics. Used to have labs that looked like this, and they started to look like Modloc lasers. So we got interested in this and said, that's really cool. We should do Poleshaping with this. And there were a lot of challenges, but we set out to resolve the individual lines and shape them. And so that happened. The first paper was around 2005. A better cited one is in 2007. But so just an example where here we had about 100 plus lines, and we put on these different phase structures that the main point is they varied rapidly from one line to the other. Lines now are 5 gigahertz apart. We can now make waveforms. The one waveform period is this, and you can't just draw one. They kind of go on forever. They coherently overlap with each other. And the stability depends a lot on the pulse-to-pulse phase stability that depended a lot on the frequency stability here. So they kind of start to touch the concepts that led to the Nobel Prize. But what the last part I really want to tell you about is, well, what about these frequency combs? Could you make them from really small devices, not Modloc lasers, but from microresonators? So this has become a very hot topic. This was started off by a group in Switzerland in 2007, but these are all different pictures of optical microresonators, things that this may be in silica, some of these are in crystals. The work that Cornell introduced and that we do at Purdue with Minghao Chi are in films of silicon nitride, but you have different structures that trap light. So for example, here is introduced by a waveguide. It would come into this ring and go around for a long time. Okay? In the bulk devices, people can make quality factors of 10 to the 9th, which is completely heard of in the RF domain, but you can do it in optics. In planar integrated optics, more like 10 to the 6th. We recently got up above 10 to the 7th. And so in a resonator, you come in with relatively weak light. It gets a lot stronger inside when you're in resonance. Then you get nonlinear interactions. And what was found is that these nonlinear interactions can create gain and populate new light on a lot of, this is where the light started, on a lot of different frequencies at different resonances. And ideally, you can think of these, once you get some of these, they mix in such a way they replicate the frequency, and you might be able to get up with a very evenly spaced frequency comb. Okay, and so, yes, but there's a lot of things that can go wrong, as many of us now know. Okay, and so these are just some of the nice pictures of different resonators where we really try to engineer some functionality into the devices, let me say. But so let me talk about this a little bit. And so what I was interested in for the first time in this field is, I clearly care about the time domain aspects. Frequency does good, but I like the time domain aspects. And so in this cartoon of what we did, we send in a single frequency laser that we can tune into resonance. We get it right, we get a comb of frequencies, so that's shown as white. And then the output, this is kind of a weird picture of a pulse shaper. So we use pulse shapers to try to shape those into short pulses. We measure it and ask, one, can we make short pulses? And B, do they act like Modloc lasers? Modloc lasers we can manipulate, we can shape, their phases are coherent. We can find out to what extent they're really even coherent signals. So what do we find out? The answer is sometimes yes and sometimes no. That was actually a little bit of a surprise. I thought they were going to be like Modloc lasers, and sometimes they are. Okay? So in some cases, we got a comb of, this is maybe 1-2 dozen frequencies, not so many. When it comes to the laser, we measure something that looks like this in time. It's not very pulse-like. But it's not because it isn't coherent, it's just because the phases aren't right. So with a pulse shaper, we can play with it, try to peak up the signal, and eventually get something that's about the best you possibly could with that spectrum. So that says it's phase coherent, and we've controlled the phases to be almost flat. And so this is the first demonstration. They could be fully compressed into femtosecond scale, nice coherent signals. The surprise was it was sometimes no, and with some other combs, and we recognized some differences in the ways the combs got started. Sometimes you'd get these signals that you could sort of play with, but you couldn't ever drive to zero. And what that means, all these measurements, they're kind of fancy indirect measurements you do in ultrafast optics. It's not just like a sampling oscilloscope. And it basically means when you can't drive this to zero, it means it's only partially coherent. And it really means there's a large part of fluctuating intensity noise. Okay? And by the way, sometimes then there's more extreme cases. These are pulses we can make beautifully clean. These are pulses that aren't beautifully clean at all. The green one is the experiment, and half of it is clean and half of it isn't. And so if somebody reads my book in Ultrafast Optics or takes my class, that's the signature of something that's just continuous Gaussian noise. It's not a pulse at all. Okay, so this created a lot of effort in now this growing community among ourselves and several other groups on how in the hell do you control this? How do you find ways to sort of make your combs coherent and broadband and well-behaved? Okay, oh, by the way, why is this important? It's probably obviously important, but it turns out there's strong correlations with the noise. And these same combs that we could either compress or not compress, if we try to use them for optical communications by grabbing one line at a time, so this could be a source for multi-wavelength communications, modulate at 10 gigabits per second and superimpose the results into something what people call an eye diagram. Basically, when it's coherent, it's slow noise, and you can make these eyes, you can imagine you do threshold, you can always know if it's a 1 or a 0. So we could do error-free communications. In this one, you try the same thing, and it's just people say about the eye is completely closed. And that means the noise is so bad that we try to measure the bit error rate, and 50% means there's no information. But the bit error rate stops working, the tester stopped working a little bit before you get to 50%. It stopped working. So this is important. Okay, so I think we've got like 2 more, and I'm going to, we'll be almost in time here. So there's a lot of progress among a number of groups, and we're one of them, but there's a number of strong groups who are making rapid progress now, figuring out ways to look at the coherence, how to make them more coherent. Here's an example where we put one of these heaters on the microring that helps tune the resonance laser detuning frequency, which is a very important parameter. And one of the recent results we're still under review in our group is we have a transition from this sort of ugly-looking comb to this comb that's much more broader band. There's hundreds of lines here. But the important thing, this one is incoherent. And if we look at just the intensity noise at low frequency, here's the baseline. Here's all this intensity noise. It's one of these really useless combs. But by kind of adjusting the frequency drive and power parameters, you can make it suddenly transition to this very quiet state. So people call that mode locking. Really, there's a lot of nonlinear dynamics that we in the community are learning how to navigate. And if you work in this regime, you find that you can compress it into beautiful pulses. And one of the things we do in this pulse shaping that I didn't really illustrate before this is we know how we have to program the phases to get pulses. That means we know actually what the phases were coming out of the microresonator before we did it. So we can reconstruct the waveforms. And so we're the first to observe clearly something we're calling a dark soliton. It's a pulse with this negative thing here. This is a thing that I kind of knew about from about 25 years ago in different lines of research. It's got some interesting frequency modulations, and there's some other distinctions. We're the first to recognize you could do this in what's called a normal dispersion microresonator for a long time, well, 3 years. Everybody's saying it has to be a certain sign of a dispersion. It doesn't. Okay, so where is this going? Again, maybe 2 or 3 slides here. We're close. So I just thought I'd advertise one of the projects we have here. This is one of the sort of the biggest current funding in our group, something called the DARPA Pulse Project, which has either pulse sources, combs from microresonators, or people with giant lasers trying to hit targets and make neutron sources. So we kind of have 2 classes of femtosecond people. But there's a number, most of the top groups, 4 or 5 of us are supported on this program for microresonators. What we're trying to do is fuse this with our interest in RF photonic signal processing. And so we're not make waveforms, but we also make filters based on photonics for RF signals. And we like comb sources to do that. So I won't talk about this at all. But the point is right now we have some techniques that are really very cool that we originated. We've been working for 5 years. And we have combs that look like this based on lasers and lots of telecom modulators and watt-level electrical drives. These make very nice combs, but they're big. And we'd like it to look like this. So we're partnered with a company called Infinera, which is the leader in photonic integrated circuits. The lead there that we partner with is a guy named Fred Kish, who some of you know spent some time talking to us in the past. And so what we're doing is trying to take with Ming Hao and I, take these silicon nitride microresonators, despite the fact that we only partly understand the physics and are still getting better at controlling them to where they can be useful. We embarked on trying to make them compatible with indium phosphide integrated circuit drive lasers. This involves big challenge powers. We have to reduce the operating powers by about 10 times. We're partway there. And we also want to have indium phosphide-based integrated circuit pulse shapers. And this is something Infinera is very good at. And the idea is we're going to do it, and in sort of the next phase of the program, they're going to start taking over the packaging. And the hope is that it ends up, the promise is that we'll end up with something like this is one of the commercial lightwave transmitter modules, so it's about so big. And if we can succeed with this, we'll learn a lot and definitely help sort of push the technology. I'm only going to show one thing here without any of the results. But I mentioned quantum optics, and so Vlad Shalev and I and Sasha was here and a few others. We have this preeminent team led by Vlad trying to build up quantum photonics at Purdue. And so this is, I would share that we've sort of gotten interested in the last 2 or 3 years. And it turns out pulse shaping can work with quantum optics systems. And I'll say it's interesting, these aren't short pulses, but it turns out if you send a certain light into a nonlinear crystal, the photon can break up into 2 frequencies. They're roughly each half the original frequency. But they don't have to be exactly half. So it sort of breaks up into sort of these 2 different pathways. You get 2 photons. Where the frequencies are of the photons is completely probabilistic, but you know if you know the frequency of one, energy conservation says you know the other. And so the frequencies of these two photons might be correlated, anti-correlated like this. Turns out they're also time correlated. You don't know when you're going to get one of these rare events. Whenever you get one, you get the other. And so it turns out there's a tight time correlation. In the systems we work with, that's sub 100 femtoseconds. And you get this tight frequency and time correlation at the same time, but in kind of a non-classical quantum mechanical way. And so let me just say it turns out that you can shape the correlation functions. And so it turns out if we put these sort of signals through Poleshapers, the same way we put on phases that shape deterministic intensity waveforms, we can shape these things that are really just conditional probability functions. Okay, we can shape the time correlation functions between the photons. I'll just flash through. There we can make these things. We can do them in pairs so that they compress, and so that's sort of a quantum mechanical version of dispersion compensation. We can do these other things that's sort of like coding and decoding, and maybe could be useful in multi-access quantum communications. Maybe, I'm still looking here. There's a lot of questions of whether it's actually useful, but we're playing with it. So the last one is I just want to say, what about service? I won't go into it, but particularly for all the students in here as you go on into your careers, it's not just about research. It's a lot about research, if that's the way you go. But I think I always felt service was important, and so both internally and externally, I've tried to get involved in a significant way. And so this is just to speak about that. One example, I'm the editor-in-chief of the largest journal in terms of 3,000 papers a year in the ISI optics area. Why do I do it? It's one, because I like to publish there, but because somebody has to, and I was asked, I realized I hadn't done anything like this for a couple of years, and it was an interesting challenge. Okay, but again, for the young people as you develop, try to find some time away to help where it is, or you're working, or where it is your technical community, et cetera, as well. And so thank you. Just a few snapshots I get from collections on my website. This is the most recent one of some of the students doing all this work. So again, thank you for coming.
I'm sure Professor Weiner will answer some questions. Anybody? Yes.
Andy, you're so handsome. Well, you're still very handsome, but when you were young, it was almost like irresistible. Thank you for not switching to modeling. I mean, but as accomplished as you are, when you don't sleep well, I mean, what do you challenge yourself with? What you're thinking? What is your next goal to accomplish? I mean, like big goal. So what is you really preoccupied to you? Like, let's say in 5 years, where would be the next breakthrough you're thinking about now?
Well, yeah, that's a good question. I've always had a sort of a hard time organizing my research that way. If I could organize it that way, I could sell a lot more programs to DARPA. But usually the way I do it is there's something that gets me interested. And I play with it, see what we can do, see if it opens up more possibilities. So this one I talked about just a little bit, the multimode fibers. I don't know if that's going to be the right vehicle, but really this idea, we've really branched off into some aspects of wireless communications with a lot of synergies between ideas we've developed in optics. Really the idea is, can we find an interesting vehicle that will be novel compared to a number of very active areas others have gotten involved in, that will really bring our strengths and start to look at random propagation of broadband fields in the optical domain. So maybe, the multimode fibers, maybe we can use it for delivering light in a biological scattering medium. And in the last few years, people have started to bring MIMO techniques to optical communications and allow them to start to look at few mode fibers to try to pour more information down. So the thought is, maybe this is an interesting area. Exactly what we're going to bring to it, I have no clue now, so sorry about that. You'll help me figure it out. So that's one thing. I think the other one that's clear is we're, I think, sort of doing this kind of, short pulses and broadband, interesting signal processing. For a long, I was probably a little bit slow getting involved in micro and integrated systems. But I think where the field now is probably essential. There's a lot of momentum that way, and I suspect there'll be lots of interesting things to do, provided it's in the context of integrated and micro implementations, for the next 15 years. So the micro resonator is one. What else will do that, we'll see. Kind of interested in bringing that into quantum optics work as well. But I think that's an area that's going to be important for us to become even more active in. Okay. Good.
Anything else?
So, and we know that you build up the team together with Professor Schleif on want to push the quantum optics center in Purdue. So I would ask, what's your vision on this quantum photonic, quantum optics and quantum photonics? So what do you think? What would be the possible and what would the achievable goal, like in 5 years or 10 years, like within this field?
Well, probably as you know, Professor Schleif gave the successful pitch to have these teams, and he was talking about, for example, single photon sources. But I think certainly the idea of experiments we've done, my group so far use bulk Poleshapers, and there's a little bit of fibers and some integrated nonlinear optics, but mostly it's kind of bulk. And there's a lot of interest in trying to bring, what we brought to bear to some of our ideas out of ultrafast optics and telecom type of technologies, and we've, I think, brought some interesting to the field. There's a lot of growing interest, and I think it's very important to find integrated platforms, for doing that. So otherwise, the same answer as before. It seems like an area where there's a lot of opportunity and possibilities, and in just terms of manipulating signals in a way that's much different than the past. The way I see it, we need to have increase the number of strong people interact with each other, and probably what will really important come out, which is hopefully something, will not be necessarily something we precisely predicted. If I knew more precisely, we'd be doing it right now.
Just remember, Andy, you're still very, very young. You should set really huge goals ahead of you.
I appreciate that. Thank you. I'm probably at least a few months younger than you, isn't that right?
Yeah. And I feel very young. So
very good.
You should feel even younger.
Excellent. Okay, good. Thank you very much, everyone.
Thank Professor Weiner.
Okay.